So one thing I did at university was a function generator, and that was my senior design project. That's why I want to make this video in case somebody else is trying to build a function generator. Maybe they can see kind of how we approach. So I guess there's two ways just to split it up into two parts, analog and digital. We ended up going with a digital solution. Another thing you might want to consider are the specs or the specifications. That's going to come up and that's going to change kind of as you build. The hardware is going to be kind of the limiting factor here. So we might even leave that on to the last part. But I guess the main idea is that we have some sort of MCU or chip that has GPIO functionality, and we can consider these as bits. Bit 0, bit 1, bit 2, bit 3. We have these 4 bits. How do we turn this into an analog signal? And there is a component called a DAC, so the digital to analog converter. And that's exactly what we need. So we can put those inputs in here and we'll get a analog output here. I'll just call that A0. So if we put in, if B0 is 0, 0, 0, 0, so let's just do 0, 0, 0, 0, 1. Maybe that corresponds to some kind of analog voltage, maybe 1.25 volts. So let's actually go into kind of how this would work. Obviously in our solution we also had a power converter here. I think we ran ours on USB, so we have a USB connector, and I think we get 5 volts. Put that down to 3.3 to drive the MCU. We had something like that, I guess, a converter. Yes, and we also had an op-amp stage here, so the gain times our analog output. And we also had a potentiometer here. One thing to keep in mind is the op-amp slew rate. This will dictate how fast your frequency is going to be on your signal generated. But let's look at the DAC for a minute. So we would have the codes on a 4-bit DAC. I guess it'll look something like this. These are a couple of numbers. Okay, so let's call this the bit code. Let's call this the analog value. So let's just say this is 0. And you're going to need a reference voltage. So if it's 5 volts of reference, then you have to divide that by 5 divided by 2 to the power of 4. So that's going to give you the voltage increment per bit code. So let's do that calculation quickly. 0.3125 volts per bit code. So this will be 3125. This will be 3125 times 2, 0.625, and so on. Up to eventually you would have a bit code of 111, and that would give you 5. Because that's the reference voltage. Now, another thing you have to think about is that these voltages do not dip under the negative. So even if you would run your code up and down from, let's say you have a for loop, and it just runs the bit code, so up and down this list, you would get a sine wave. Let's just say something like this. It's a little sloppy at the end there, but each increment here is going to be 0.3125 volts up to 5. So we have a 0 to 5 kind of sine wave here. And as you can see, the more bits you have here, the greater the resolution and the finer your final waveform is going to look like. Now, one solution that I used for getting the waveform here to look like this was to use a summer with a reference voltage of 2.5 in this case. So let's say we have a voltage source here of 2.5 volts. If we plug in this code here, 0, 0, 0, we would plug in 0, and let's this be our input here, V in. Let's say we put 0 here, then that would be 0 minus 2.5. So that's going to give us minus 2.5 volt. And as we go down the bit code, eventually we're going to have 2.5 volts. So if we put in 2.5 volts here, that's going to cancel out with the reference voltage we have, or the biasing voltage we have on the negative input here. So that's going to be 0. So now we have a different kind of table where this will be, so this is if you run it through a summer. So let's just call that A1. So you would have negative 2.5 here at this code. And at 2.5, you would have 0. And then at the final, you would have 2.5. right? Because you would put in 5 volts, it would go into the summer, and you would have 2.5. So that's how you get this below zero waveform. Then you can use another op-amp stage to kind of shift or stretch these gains kind of up and down in amplitude. You could use your for loop to be slower, and in this way have the illusion or the appearance of a slower waveform in terms of frequency. So you can alter the frequency with delays in your MCU processor code. You could, and if you have a potentiometer here, you can change the gain, and we can change the frequency. We can build different functions for different waveforms. So you could build a for loop that runs up the code and then goes immediately to zero. So that would give you a sawtooth kind of waveform. So you can build this with no issue. This is all going to be software determined. The question is, do you put some kind of filter at the end? The problem with that is the capacitor is frequency dependent. So it's going to attenuate differently depending on how fast you're running your waveform loop. So just keep that in mind. But this would ultimately be the op-amp DAC MCU USB powered function generator in very general terms. Hopefully this explanation is adequate. I think in order to understand this explanation I just provided, you would have to have some kind of background in electronics or be doing your senior design project as you're watching this. And that's kind of the target audience for this video, is someone who's trying to build a function generator and that has some form of EE background. Because otherwise I would have to go into deeper detail on, for example, the DAC, which I will in maybe a next video. I would have to go into detail of the op-amp, which I can also do. The summer, which I can also do. But there's also a lot of code for this. And if you're using an MCU, or it's going to be a lot easier with an Arduino, because then you can just use that library and build. You can do digital write, and then you can dedicate 3-4 pins for your bit output code. You can also build a DAC very simply with an R2R ladder. So let me write that down in case you need to research good, cheap DAC topologies. So this R2R ladder is just a resistor network that'll give you the DAC functionality. So you don't have to use an IC here necessarily. You could use an MCU, maybe an STM32, with plenty of pins and plug all those pins into a DAC that can handle all those pins. You can get very fine resolution if you want to do it that way. Or if you use an Arduino, you can put 2, 3, 4, 5 pins aside, run it through an R2R ladder, and you already have something going. So that's an easy way to prototype it, with an Arduino and an R2R ladder. I guess that'll make more sense if you didn't know about this. Once you look up the R2R ladder, and once you get going, you'll see kind of what I'm trying to explain here. The drivers for an MCU, I've written a few drivers for STM32s. That's a whole subject for itself. You would have to go into... You could use the HAL, the hardware extraction library, and get going pretty quickly. But if you want to extract more speed out of your MCU, you might want to do the drivers in C from scratch. So you're going to have to go into each register, toggle the bits there to get everything set up. Then you would have to create your own functions. I guess you can create your own header file, create all the waveforms, and import those in your main loop, and have some sort of super loop. The question is, if you want the user to change the waveform, you could use some sort of potentiometer analog input. So let me see if I can get this. So you can have a potentiometer, and I'll just draw that as a voltage divider. We can do 5 volts here or 3.3, doesn't matter. And this is going to be the input of your MCU. So you can set aside an analog input, and you can divide this voltage region into 4 parts. So I think half of this is what, 1.15. So what's the half of this? I don't know off the top of my head. Oh, 0.675? I don't know. But you could have a switch case, switch. It'll check a variable. Maybe I'll just name it input. And you could have a case for input less than, let's say this. And that can toggle your triangular wave. And if you put that potentiometer on a PCB with some good masking, you could get an interesting kind of setup here. Square, sine, PWM, let's just do that, for example. So you turn this pot here and it'll kind of select. I think people even add a little bit of kind of an arrow here on your potentiometer. So you can kind of select the waves like that. So that's one mechanism maybe for, so you could have a switch case running in your super loop. It checks the input in the beginning on the analog pin, finds what waveform it is. You can also do a switch case to find what frequency. So you can duplicate this setup right here, but do it with a frequency instead. So let's draw that out. 1K, 10K, 100K. Maybe you can get 1 megahertz on this setup. Who knows? Depends on the op amps and the slew rates you're getting here. So that's kind of what we did, and we ended up with a function generator that kind of looked like a little box where we had the waveform potentiometer, the frequency potentiometer, and the gain potentiometer, and the USB connection. I'll just draw that as a little box here. And then we had the two output kind of cables that came out here. Yes, we actually even had an LCD, but keep in mind that if you're having an LCD on your function generator, it might actually slow down the super loop. So you might want to look into FreeRTOS in that case and schedule a task to display the frequency. So that's kind of what we had. We had frequency here. It was a 16 by 2 LED. So we have frequency, and I think we had some other measurements here. I don't remember. Maybe it was the voltage output. Yeah, hopefully that kind of gives you a brief little overview of kind of what a digital function generator kind of looks like and how it would operate. I see there's a possibility here for an offset as well. So you can have this input here as a variable, as a voltage, its own dedicated voltage that you can use your MCU to produce. And you can this way also with a knob switch case in your MCU code, and you can have a variable offset as well. We did not do that, but nothing stops you from doing that. Yes, I think I will continue this series and kind of go into deeper detail. We can even look at a PCB and how to actually build this from scratch. I'll see if I have the time for that. I hope I do, because I think it will be very valuable and helpful for you if you're just starting out and building your own function generator. So that would be cool. I'll see if I'll have the time to do that. Thank you for watching. I'll hope to produce the deep dive into these components soon.